Hello everybody, myself Jyoti, and today's lecture is about protons and antiprotons. Basically, we are going to discuss about the discovery of antiproton. This name proton, it was suggested by Rutherford. We know that mass of proton, it is approximately 1.36 times that of mass of electron. The charge of proton and charge of electron, they are same, only they differ in terms of uh, like charge on proton it is positive, charge on electron it is negative, but magnitude is same and it is 1.6 into 10 raised to minus 19 coulomb. Proton, it is a fermion with intrinsic spin half, and it has a magnetic moment of 2.79275 nuclear magnetons. So basically these are few basic properties of proton which we should know. Now when in the last lecture when we discussed about electron positron pair formation, we calculated how much energy will be required, and that energy was equals to 1.02 MeV. How we calculated that energy? We know that mass of electron, rest mass of energy is given by mc square. If we substitute the value of mass of electron in that, you will get the energy 0.055 electron volt, and for pair formation it will be double of that, so that is how 1.02 MeV. As mass of proton, it is approximately 1836 times higher, so naturally we will need 1836 times higher energy for the proton antiproton formation, pair formation. Now as we also discussed in the last lecture that electron and positron, they are antiparticles of each other, not because they have all the properties same and they just differ in terms of charge. When electron and positron they combine, they annihilate, and that is what the meaning of antiparticle is. So the proton also has counterpart or has a antiparticle which differs in terms of charge. So when we take the proton antiproton pair, when they also undergo annihilation reaction. So the detection of antiproton was difficult because for the detection of antiproton we will need energy which will be around 2000 times higher, which was required for electron positron pair formation. So until 1955 we were not having any kind of a particle accelerator which can give, which where we can have this much amount of energy. So the evidence for the antiprotons could be obtained only from the cosmic ray events in photographic emulsions in cloud chambers. But when 6 BeV Bevatron at the University of California was built, then it was possible to perform an experiment for the production and detection of the antiproton. So this is a Bevatron. Okay. So what are the requirements to make an antiproton? So creating an antiproton would also require simultaneous production of proton or neutrons. So proton combines with another proton, it gives 3 protons plus antiproton. So this is a reaction. Now mass of proton, it is of the order of 938 MeV. So minimum energy required to get an antiproton is 2 times that, so around 2 giga electron volt. In those days, instead of using giga electron volt, physicists they typically used to say BeV, billion electron volt, instead of GeV, and that is why the name given to the particle accelerator is BeV, Bevatron. Now so with the Bevatron it was possible to detect antiproton. Now the antiprotons had to be found in the large background of negative pions. Negative particles were deflected and focused by magnet M1 and quadruple focusing magnet Q1. The particles pass through scintillation counter S1. So this is the arrangement. So we have C1, C2 which are Cherenkov detectors, S1, S2, S3 which are scintillation counters. Then we have M2 and M1 which are magnets, and Q1, Q2 they are quadruple focusing magnets. So here the particles were again focused and deflected by Q2 and M2 on their way to S2, and by measuring the time of flight between S1 and S2, antiprotons could be distinguished from pi minus, because negative pions and antiprotons they have different time of flight. So for antiprotons the time of flight it is 51 nanoseconds, and for negative pions 40 nanoseconds. By checking the time of flight for the two, you can distinguish whether it is antiproton or negative pion. Now, how antiprotons are produced? Protons from 6 billion electron volt of energy are incident on a copper target, and protons from the proton beam, they combine with the protons from the copper target, and then antiprotons are produced. So basically the collision takes place between the incoming proton and the proton in the target nuclei. So P plus P, it gives you 3p plus p bar. So negatively charged particles were selected by mass spectrograph consisting of a series of deflecting magnets, focusing magnets, scintillation counters and Cherenkov detectors. And this selected beam of particles was expected to about 50,000 negative pions to every antiproton. So you can imagine that for 50,000 negative pions, we have one antiproton. These particles all have same momentum 1.19 BeV per c and thus travel in a magnetic field, and their trajectory will also be same. Because of the larger mass, the proton had a velocity of only 0.78 c while pion had a velocity of 0.99 c. So what we basically do here is see visual confirmation. So look at these two pictures carefully. एक second. So this looks like a star. So left image and right image, both the images are same, and they are looking same, and this is a visual confirmation of the detection of antiproton. Now left picture is the annihilation star from an antiproton viewed in the photographic emulsion stack experiments, and right picture is a bubble chamber image. So the antiproton enters from the bottom. Upon striking a proton, 4 positive and 4 negative pions are created, so that looks like a star, and that is called as annihilation star. Sometimes there would be two different mesons passing through the two counters in such a way that a pulse from the second counter would be produced just 51 nanoseconds after a pulse from the first. And in that case, we can think that it is an antiproton, but basically that is a meson. And so as to avoid this accidental coincidences appearing like antiprotons, we need Cherenkov counters. So to eliminate the difficulty of mesons, which can be counted as an antiproton, we use Cherenkov counters. So we use two Cherenkov counters. One is C1, another is C2. C1, it is made up of C8F16O and it has a refractive index 1.28, and it is designed to respond to particles with velocities greater than 0.79 c. Any pulse from C1 cannot be due to an antiproton having velocity 0.78 c because it can detect beyond 0.79 c. The second Cherenkov counter, it is made up of fused quartz and it has a refractive index of 1.46 c, and it is designed in such a way that it can respond to particles whose velocities will be between 0.75 c and 0.78 c. So from C2 you can detect antiproton, from C1 you can detect pions, negative pions. So how annihilation of a proton and a neutron is different from annihilation of an electron? So in case of annihilation of electron positron, they annihilate and we get a energy. But in case of the annihilation of an antiproton with a proton or a neutron, differs in a way that several charge and neutral pi mesons together with protons and occasionally deuterons and k mesons are usually produced in this reaction. So this is all about the detection, discovery of antiproton. Thank you so much.